Oh, okay, now it's working.
Right.
Hello. Sorry about that. Something weird happened in my personal meeting room link was different in different places. I don't know why.
I don't think this is your personal room, right? I think this is a different room you set up
Oh,
specifically for the seminar.
well, that would explain why it wasn't working.
Possibly.
So I was just sitting in my personal meeting room just waiting. Are you going to be
Uh,
able to join us for the whole time, Tim?
yes.
All right.
Yes.
All right. So do you mind sharing?
Yeah, this is fine.
All right, cool. Let me try to share my slides. I see we've got Devesh here. Hello, Devesh.
Hi, Glenn.
I shouldn't take too much time. I'm going to try to not even annotate so that I don't get
Okay.
like carried away explaining too many things that I'm just
Yeah.
previewing for later.
I've prepared for 45 minutes. So we'll see.
Okay, okay. So maybe I should set myself an alarm in 15 minutes and be like, or 10 minutes, so I know when to stop.
Do you want to get going pretty soon?
Yep, let's start ASAP.
All right. And we're all, yeah, it's already recording automatically, isn't it? Yes, it is.
Yep.
All right, I'll get going then. Good morning, everyone. Thanks for joining us again for our seminar series. Recall that we're going through the Willmore flow and Willmore-related things this seminar. Uh, Today, primarily, we're going to have Devesh Rajpal speak about the Willmore flow and the existence of a Willmore torus, but Glenn is keen to add a couple of extra asterisks to his last talk before we get on to Devesh. So take it away, Glenn.
Thank you, Tim. And I'm just going to take a little bit of time to talk a bit about just to finish up the Bryant section to show where Bryant slots in. And I'm just going to really give an overview. It's not going to be much detail here. Okay. So the Willmore flow, I'm sorry, I'm just trying to set up my desktop. The Willmore flow is the steepest. Maybe I can do something. Does this work? You guys can see that little red dot thing, right?
Yeah, indeed we can.
Okay, cool. So we start with the Willmore energy, which we've seen is integral of h squared times a constant. And then our goal is to study again, like with Bryant, Willmore surfaces. And so Willmore surfaces are critical points for the Willmore functional. And the idea with the Willmore flow is to study them dynamically. So you start with an arbitrary immersed surface and then uh, evolve it so that you minimize its Willmore energy. Now, if you think about the space of all immersed surfaces, there are many ways to do that. It's an infinite dimensional space. It's a very complicated space. And so you need a way, like a method for deciding what is steepest descent. And that is where you need to choose a metric. So with the Willmore flow, we choose the L2 uh, invariant metric, which I've called L2 d mu. And this choice, okay, this choice does yield the classical Willmore flow. We can talk a little bit more about that later. Combining this metric with the first variation identity, which is metric invariant, gives you the gradient flow. All right, so once the flow starts going, we can ask ourselves the basic questions like does it exist and how long does it exist for? What happens to it? Does it reach a singularity? Does it always converge? What does it converge to when it converges? Things like that. And there is not a lot known, to be honest, about the Willmore flow. There are several papers or many papers on it, but it still remains quite challenging, especially in the realm of singularities. In this seminar series, we're talking about Kubert and Schätzler's fundamental contributions to the flow. And these are in the realm of concentration compactness and convergence and removability of singularities. So one of their first results that they proved, possibly the first result they proved, was about concentration compactness, which gives you this alternative between concentration of curvature at arbitrarily small scales and compactness of the flow. Okay, so what does this have to do with Bryant? What Bryant does is Bryant classifies the Willmore surfaces that Gubert and Schätzler's analysis produces. Okay, so let's keep going. This is just setting a notation again. I'm going to skip it. We've seen all this already, but if you haven't seen it and you're watching on YouTube, then you can pause the video and read this. That's the purpose of this slide. Okay. So what is this L2 d mu metric? Okay, so in the space of all immersions, a metric is a smoothly varying, and Riemannian metric is a smoothly varying choice of inner product, and on the tangent spaces. And the tangent spaces are vector fields along that are sections of the pullback bundle of the tangent in R3, right, along the immersion F. That's what this notation means. We can split these vector fields into normal and tangential parts. The tangential part corresponds to reparametrization, and so we don't care about it. And so we only take the normal parts, and we can build this thing down here, this weak metric. It's not really a metric because we've only taken normal parts. And in fact, if we use this metric to then define a metric space, that metric space turns out to be the absolute worst metric space you could possibly imagine. And I'll just leave that as a cliffhanger in case people are curious about that. But still, that's what we did classically to define the Willmore flow. So that's what we're going to do here. And it's the simplest kind of metric that you could imagine on normal vector fields. Okay, now I'm going to go through this. One of us is going to go through this in detail. Or actually, I think I did do this in detail in one of my earlier talks. My memory is just awful. This is the first variation, and you can see that after integration by parts, it has factored very nicely with respect to this metric, right? So you see we've got this metric structure, this L2 structure, and the psi here is going to be this operator E, which we can write using the trace-free second fundamental form like that. And then your standard definition of gradient with respect to a metric is the following. On the left-hand side, we've got this expression here. On the right-hand side, we've got the metric product with the gradient and an arbitrary variation. And so we can identify these two things together. And so we get that the L2 d mu gradient of the Willmore functional is this operator. Okay, and so then that gives you your flow. Steepest descent L2 d mu gradient flow for the Willmore functional is this one. And that's basically how Kubert and Schätzler write it. Okay, except they do in arbitrary codimension. In high codimension, you look at the induced Laplacian on the normal bundle, which is why there's a perp here. And you have the Willmore, you have the mean curvature vector. And then this A0 squared is not so simple. It's a Q. Has this expression. But you can see that if you're in one codimension, it collapses down nicely to A0 squared. Okay, which is what I wrote down here. All right. So I don't want to take too long, but along the Willmore flow, by definition, this is what makes it a gradient flow. We have monotone decay of the Willmore energy, and it's proportional to its Euler-Lagrange operator in L2 squared. We have a natural parabolic rescaling, and what we're going to show later is this concentration compactness alternative, which is itself inspired by work of Michel Struve on the harmonic map heat flow. And it says that this concentration functional, if it's finite, and if A is in L2, right? So if A is in L2, then we can always make this arbitrarily small by reducing rho. And in so doing, we can extend the flow. And so in other words, the only way for the flow to become singular is that this concentration functional blows up at all scales. And so that gives you a wonderful quantization of the curvature at a finite time singularity, which is this epsilon 0 down here. Right? So this is a universal constant. Okay, so that fully characterizes singularities for the flow, but it doesn't give you any qualitative information about what they look like. It doesn't tell you when they can happen. For example, it doesn't give you a correspondence between initial data and singularities. It just says that if they happen, they have to happen in this way. It's still very powerful, and by taking a blow up sequence, you can look at what's called the blow up. It's not algebraic geometry blow up, but it's the blow up of the flow. It's a limit of rescalings, and you can look at the equation that they satisfy. The key observation that Kubert and Chesler make is that the energy identity gives you this integrated inequality, and the TI here can be chosen very carefully along the sequence so that the right-hand side vanishes fast enough such that this thing inside the integral has to vanish. And so you eventually prove that the blow-up is a Willmore surface. And then that's where, well, if it's a nice enough Willmore surface, then you can use Bryant. If it's not, then you need to prove some more things. Yeah. And so, yeah, I've got this little contrast with mean curvature flow because that's my time up, by the way. This little contrast with mean curvature flow because if you come from mean curvature flow, then you might be a little bit confused because you would expect to see shrinkers as your singularity models, and you would also expect to see some type 1, type 2, something like that. That doesn't happen here. Right. Here, our natural energy that we're defining the flow with respect to is scalar invariant, right? So the mean curvature flow is defined as the L2 d mu steepest descent gradient flow for the area functional or the volume functional, depending on your perspective. And that's not scalar invariant. So it's quite different. That's where we suspect the difference is with the singularity models. It's just an intuition, really, but I think it's quite useful. Okay, so that basically is what I wanted to say. There is this removability problem that Kubert and Chetzler study in their Annals paper, and that is to prepare for the application of Bryant. That's where Bryant enters. Yeah. Okay, so there's my little flow chart. I'm done now, so I'm happy to hand over to Devesh. Or if there are any quick questions, I guess, or we can save questions to the end. I don't mind.
Yeah, but maybe while you stop sharing and Devesh starts sharing instead, if there are any quick questions at this point.
Yeah.
All right then, Devesh, do you want to start sharing your screen? Thanks all. Thank you, Glenn, for taking us through those last few remarks. Now we're going to have Devesh, who's going to speak to us about the existence of a Willmore torus. Thank you, Devesh.
Good morning, everyone. I'll be speaking about existence of Willmore torus and arbitrary codimension. This is a result by influential result by Leon Simon. It differs from at some parts. The theme is a little bit different from what Glenn has done so far. We are not going to be doing Willmore flows, and the previous work in Bryant setup is restricted to codimension 1, but the Simon's proof here is very general. We are going to prove a very powerful theorem in arbitrary codimension. Yeah, and okay, so I'll begin. So recall the setup. We take an embedded surface in Rn and define the Willmore functional as this. My notation will differ from Glenn, is that I'm taking my mean curvature vector to be the sum of principal curvatures and adding a quarter factor in front of the functional. Yeah, so this is my Willmore functional for an embedded surface. And as you saw in the last 15 minutes, the Willmore functional is scaling invariant. Moreover, it's also translation invariant, and there's a much bigger group acting as a gauge group here, which is the conformal transformation of Rn. So it's invariant under the whole Mobius group in Rn, which kind of makes it tricky to understand. Yeah, and suppose now we want to understand its minimizer among the class of genus G surfaces. So this will be my notation. For surfaces with genus G and living in Rn, which is going to be fixed for the rest of the talk, I'm going to call beta superscript n subscript G the infimum among all such or among this set of surfaces of genus G. And it is known that beta has a lower bound of 4 pi. This 4 pi is achieved by the round sphere. And there's also an upper bound of 8 pi. The main theorem with Simon proved in 1993 is this. So for any n bigger than or equal to 3, one can find a smooth real analytic and embedded torus in Rn such that the equality in the previous infimum is achieved. So there exists a smooth real analytic embedded torus in Rn, which minimizes the Willmore functional among all the embedded tori in Rn. And Simon's construction, the theorem as stated is for torus, but the construction almost allows it to prove the existence of the genus G minimizers, except you can take, so if you have a genus G1 surface, which is a minimizer, and a genus G2 surface, which is also a minimizer, you can take its connected sum to produce a G1 plus G2 minimizer. And the proof couldn't handle that part. We didn't know whether this connected sum could decrease the Willmore energy further. So up to this, Simon proved the existence of genus G minimizers, and later Bauer and Covert resolved this 10 years later. So they proved that the connected sum construction will not be a minimizer of the Willmore functional, and resolving this, we have a theorem that for every genus G, there exists a smooth minimizing genus G surface among all the embedded genus G surface. Okay. Yeah. The paper is roughly divided into 4 parts. The first is diameter estimates. This lemma produces a lower and upper bounds of diameter based on the Willmore functional. And this will be essential when you take a minimizing sequence. You want to control the diameter of your minimizing sequence. Then there's a technical graph decomposition lemma, which will also be needed when you take the minimizing sequence. So we are going to deconstruct our surface into bunch of graphs minus some bad parts of it. It's a fairly technical lemma. And then, yeah, this is the crux of the paper. The naive idea would be to just start with a sequence of surfaces which go to the minimizer, which are minimizing the functional, and then see whether you can prove regularity of this sequence. And you need to start with very crude construction. So Simon starts with just a measure theoretic limit, and then somehow, and after there will be a few points where you can't control the curvature. But in that minimizing sequence, we are going to prove regularity minus of the minimizing sequence, except at a few bad points, and then with some very hard analysis, you can also prove regularity at the bad points. The problem with this approach is that you can lose the topology. We are only constructing a measure theoretic limit. it cannot control the topology. So if you start with minimizing torus, you can possibly end up as the minimizing sequence may end up as a sphere. But there is a way to control this. So remember that Willmore functional is conformally invariant. So in this sequence, the last part would be to conformally changing the sequence to do some combination of rotation, scaling, or inversion, such that we can ensure that the limit is not a sphere anymore. And in this way, we have constructed a genuine, smooth, analytic minimizer, which is a torus. Okay. This talk, I'll be mainly concerned with just the first two parts, which are diameter estimates and graphical decomposition lemma. Okay. Yeah, so if you have a boundaryless surface and your surface is connected, then the diameter can be bounded above and below by your Willmore functional with some factor of the area. And Willmore functional is scaling invariant, so this matches the scaling parameters. Square root of your area matches the dimension of the diameter. To do this, the idea is fairly simple, which is to use the divergence formula. So recall that if you have a C1 vector field in Rn, the divergence formula says this equality is divergence of your vector field is equal to negative of the vector field dot with the mean curvature vector. And for a fixed y in your surface, we can take the difference vector field first to test, and this vector field will have divergence too because sigma is a surface. You can calculate this, and if we plug in this vector field, we get a fairly easy way. We get a fairly easy way to get a lower bound on the diameter. So this left-hand side evaluates to twice the area, and this x minus y can be estimated above by the diameter. And now I'm applying. Sorry, yeah. After applying Holder inequality, you can get this. There might be a typo in this. Yeah, I may have messed up the Holder inequality, but you get a lower bound of on the diameter easily. Okay. To get the upper bound is a bit of struggle. And this is what we'll do. So fix a rho and consider sigma between 0 and rho. You can see this picture here. So I have a surface here. I have a big ball of radius rho, and inside it, I'm going to consider smaller balls varying in length of radius sigma. My vector field is going to be this. So let x be the difference vector field from y, and let phi be the maximum between x and sigma raised to minus 2 minus rho raised to minus 2 and plus of that multiplied by the difference vector field. So inside my smaller ball, my vector field looks like 1 over sigma squared minus 1 over rho squared times x. And outside it, I have the maximum is achieved by mod x. So the vector field looks like this. And if you apply divergence formula to this vector field, if you apply a divergence formula to this vector field, you get a big expression like this. The divergence of the position vector field will produce xt terms, the tangential component of your position vector. But there are some other terms which will cancel the xt, and you'll get x-perp terms. And here, sigma rho, sigma subscript sigma to rho means the area between these two. So the annular cutout of the surface. Okay. Yeah, I've written it here. Okay. it's the sigma rho set minus sigma sigma. Once you have this, we are going to apply completing the square formula. So we have an x perp here and also an x dot h. If you complete the square, you get this term. The formula becomes something like this. You'll get a square coming from the mean curvature vector, which is a Willmore functional set in that annular region. And you'll get some density terms from sigma, rho, and some other cross terms. But the important point here is that if I rearrange this, so if I move my rho around and split this Willmore functional into Willmore functional of the sigma cutout and the rho cutout, I get a monotonicity formula. So if I define my gamma to be this, which is gamma of radius, gamma of r to be this area bound, plus a quarter of the Willmore functional plus a cross term, then your divergence formula will give you this equality. Gamma of sigma plus a positive term is gamma of rho. And this implies that gamma is a monotone function. And this is true for any surface embedded in any codimension one. And the terms only involve a Willmore functional term, a density term, and a cross term. So naturally, we'll want to see how to use this monotonicity formula. And we get some easy equality results with this too. So if I take the limit of sigma going to 0, say here, I'll get the density pi. There is no Willmore functional left, and the cross term can also be estimated to be 0. So h, you can consider it to be bounded. X is bounded above by r. So you get like an area term over r, which goes to 0. And the only contribution comes from the first term, which is the density term. So gamma, the limit at 0 is pi, and the limit as the radius goes to infinity is a quarter of the Willmore functional. The cross term goes to 0. The area is bounded because we are considering compact surfaces, and you're only left with the full Willmore functional. So this reproves our bound considered before, that the Willmore functional is bigger than 4 pi. And if you consider the equality case, which would be when this positive term is 0, you can prove that this only happens when you are at a surface. And the equation kind of looks like the self-shrinker equation for mean curvature surfaces. You have an x perp and the mean curvature vector, but it's way more rigid than that. This has to happen around every point in your surface. And by an application of maximum principle, you can prove that this quantity is 0 if and only if you are on a round sphere. So which reproves our lower bound on the Willmore functional. Also, the above proof can be generalized to varifolds without too much difficulty. And so if my varifolds have density theta 2, then by the same application of monotonicity earlier, I can get that the Willmore functional has to be 4 pi times the density. And yeah, the density comes from this. For compact surfaces, we only had pi coming up, but if you are on an immersed surface and this point is crossed over theta too many times, then you get theta 2 times 4 pi. Yeah, and so we recovered the Lee-Howe's inequality. And this was done by Kovac and Schetzel in the case of varifold. Okay, yeah, the small that we haven't completed the proof of upper bound yet. The only thing remaining is controlling the cross term. The cross term, which looks like this, can be upper bounded by another density term and a Willmore term. So if you plug in back your monotonicity formula, you get that gamma 0, which was pi, is less than gamma rho. And so some coefficients of your density and the Willmore functional. We have an upper bound. If now to, now let D be the diameter, and we are going to consider this scale. So we'll decide the scale rho, which is between 0 D by 2 later, and we'll consider, let N be this bound. So for this scale, we are going to select points in the boundary of this radius on your surface. So, and you can see in this figure, let y be let y be the point from which diameter is achieved. So I'll pick my y and I'll keep drawing balls of radius j plus half times rho. So you'll see 1 ball, 2 ball, 3 ball, and 4 ball here. And I'll select points on the boundaries of these balls intersecting the surface. So this is my y0, y1, y2, y3. And because I'm assuming sigma is connected, these intersections will be non-empty. So once you have selected your points, you can cover your Willmore, you can cover the surface with balls of radius rho by 2, and by the estimates above, these will be pairwise disjoint. And we are going to get an upper bound on the number of such points. So if there are n such points, then n times pi is going to be less than, then applying the previous estimate for every such point, you get this with bounds above. So n times pi is bounded above by a constant times your density. And the scale, all of area, the scale we chose, and our Willmore functional, the total Willmore functional. At a particular scale, which is this, so we take square root of the area over the Willmore functional, so that the right-hand side becomes a function of the Willmore. If at this scale, the right-hand side evaluates to this thing, 85 over 4 times the Willmore functional. And our n by construction also is bounded below by the diameter times the scale. And if you if you reapply the definition, you get an upper bound on the diameter based on the Willmore functional. This finishes the diameter estimates. So we have the preliminary result to go to the minimizing sequence proof. Next is, this is going to be fairly technical. Simon needs this result in order to control various pieces of the minimizing sequence. The idea here is that we want to decompose. We are already on a smooth surface embedded in Rn, but we want to decompose our parts of our surface into graphs, except we can't do all of that. There will be a few bad points where you cannot have the full control. So there are two parts of this. There's one with L1 bound on the curvature, and another with L2 bound on the curvature. Okay, I'll begin. So let sigma be a smooth compact surface embedded in Rn. if you have a scale for a beta, you can find an epsilon naught, which is independent of your surface and the scale. And for epsilon small enough, you assume these three things. So origin always belongs to a surface. The area is bounded above by beta, the rate of growth of area, and our L1 norm of the curvature on every scale is bounded above by epsilon. Then you can find disjoint closed sets P1 to Pn in your surface, such that the sum of the diameters of these closed sets is controlled at the scale you are on. And except these bad sets, our surface is a union of graphs. So yeah, it will be clearer with the picture later. Minus a few closed sets, our surface is graphical, which I'm denoting by graph UI. And furthermore, these graphs can be multi-valued because of the arbitrary codimension. And these, if UI has multiplicity ki, the multiplicity of the graph, then there is a bound on the sum of the ki's. And these UIs are also of small height and small gradient. So the supremum of the height of UI at the scale rho plus the gradient is bounded above by some power of epsilon. Any questions on this? Yeah. It might be confusing since we know we are at this decomposition is for a smooth surface. So we know all the paths have to be smooth, but the way we are doing is that we are only assuming an L1 bound on the curvature. And then minus a few bad paths whose diameters are also controlled. Your surface is graphical. The L2 part is a bit easier than this. So if you have an L2 bound, things get better. You can remove the multiplicity of your graphs. You can take all of the graphs to be single valued. So all the ki's is 1, and we have the number of graphs. We also have a bound on the number of graphs now. And at a lower scale, which is sigma between rho 4 and rho 2, your surface looks like some unions of disks. And so, wait, might be better with a picture like this. Yeah. So imagine this is my ball where I'm analyzing the cutouts of the surface. I have a plane Li and a plane L2, and except these bad paths, so P1 and P2 here and P3 here, the surface is graphical, which is the shaded region here. And you have a good control on the height as well as the gradient on these graphical paths. And you also have good control on the number of such pieces, as well as the diameter of these bad paths where curvature might be high and you may not be able to have good graphical approximation. The L2 case also says one more thing. So in this decomposition, all of your components are going to be disks. And in fact, all the bad pieces, which is PJs, are also going to be disks. So among these disks, minus the bad disks, your surface is graphical. And this is if you have an L2 bound on your curvature. If you have an L1 bound, the picture is a bit more complicated. But yeah, Simon needs this because you have very little control when you're doing measure theoretic convergence. And we are going to select these planes such that we are going to select points and these planes such that we can find a common plane in the converging thing, and then do these graphical estimates there. Yeah, so rephrasing, the above lemma decomposes our parts of surface into a union of disks with smooth boundary contained in the boundary of your ball. Each of the disk is a smooth function with small gradient and small height, except at a few holes, which I'll call the PIs, and yeah, which we'll also call the pimples, PIs. Also, yeah, one more thing. This lemma has nothing to do with Willmore functional so far. It's just a decomposition of surface thing, and because I don't know if this is needed in the minimal surface machinery or not, but like if you want to do the corresponding theory for minimal surfaces, like if you take the area minimizing sequence and then want to see the regularity, I this might not be needed. So I think Simon needs to come up with these lemmas, especially for the Willmore functional. But yeah, if in case you ever need, if you have a minimizing sequence of an arbitrary functional, this lemma might come into place there as well. Okay. Yeah. I don't know how much I want to go into the proof of this lemma, but the proof is divided into 4 parts. So first you find planes where the surface is graphical with small gradient, and then there's a lot of playing with parameters here. And after this step, you pick the domains in your plane, the LIs we considered, and you also pick the bad parts where curvature regions might be high. And it's done in a way such that everything is very finely tuned. You need to play around a lot with the parameters. Throughout the proof, like in this construction, you can also bound the number of graphical pieces and the diameter of pimples. And yeah, the last part is covering the L2 case. I will go through some parts of I'll go through the first point a little bit. Okay. Okay, so we start with the Grassmannians of 2 planes. So let tau1 and tau2 be unit vector. We consider their wedge, so that tau1, they are perpendicular. So this is the Grassmannian of 2 planes in Rn, and its dimension is 2n minus 4. We are going to cover this Grassmannian into balls of radius eta over 2. Eta will be chosen later, but essentially, you want to cover all the directions of your 2 planes with small radius. Yeah, then for each centers of these balls, we can consider the tilt function, which I'll call Fi. So Fi measures the tilt of the tilt at the tangent at x from the direction tau y. And this is a function on this ball cutout of our surface. Its gradient can also be estimated. And yeah, the gradient comes out to be bounded above by the second fundamental form, since the gradient is going to measure tilt. Okay. Now we are going to apply Sard's theorem. So you can find a T such that the level sets of this tilt function is a regular value. So the level sets will be some codimension 1 curves in your surface. And yeah, by Saat's theorem, uh, you can find for every I, you can find a Ti such that gamma I, these level sets of the tilt function are union of finitely many disjoint Jordan curves and Jordan arcs. I think it might be better to say it's contained in the union of finitely many disjoint Jordan curves and Jordan arcs. And you can complete these arcs such that the endpoints are only in the boundary of your ball. And for every such tilt center, we can successively apply Saat's theorem so that these Jordan curves are either disjoint or intersect transversally. And so, yeah, I've drawn a picture here. This is the cutout of my surface, sigma at scale sigma naught. And you can see some Jordan curves, which are the level sets of our tilt function. The problem is these Jordan curves can be nested. So we haven't obtained our domains yet. But the idea would be we'll collect the connected components obtained from this Jordan curve. So let Qj be the connected component of my surface minus the Jordan curves. And by construction, since so the tilt function will be a continuous function on these connected components. And I know this is level set of where the tilt is only Ti, and we have controlled Ti as well. So Ti is not too large. So once you, we can also, in these connected components, we can say that the supremum of the tilt difference doesn't vary too far. It's controlled by 2 eta. And this is exactly how we are going to find our planes. So for each of the connected component, pick a point in the interior and let Lj be the plane passing with the orientation of that point. We have found, and for each such J, we are going to select a point and a plane passing through it. And inside that connected component, by construction, my surface will be graphical with small gradient. And because of small gradient, you can also control the small height. One thing I didn't go through in this presentation is that Simon also has a way of controlling the L1 norm of your Jordan curves, which lets you control the small height. So these Jordan curves are the length of these Jordan curves, the sum total length of these Jordan curves is also controlled. Yeah, I might need a few more details from the graphical decomposition lemma later. But the next part of the paper is this. We just start with a minimizing sequence of smooth embedded curves, and because of scaling invariance and translation invariance, we can assume that our area is 1 and my surface is passed through origin, and it minimizes the Willmore functional. Then you can take a subsequence which converges to a smooth embedded surface, but there may be genus loss here. So if it converges to a surface of genus G naught, we can only guarantee that G naught is less than equal to G. Yeah, this is the crux of the paper, which will be done in the next talk. I think, yeah, I'm finished here.
Great. Let's everyone thank Devesh for taking us through this material.
Thanks, Devesh.
Thanks, Glenn.
Does anyone have any questions for our speaker?
Is there anyone? No one's brave enough to ask questions about graphical
Yeah, I can go through some parts again if needed, but the paper is fairly technical. It's one of the most challenging papers I've read so far.
Oh,
Reading,
it's very hard. It's very
yeah,
hard. It's well
yeah,
known for being very hard.
okay.
Um,
And yeah, Glenn, you can step up any moment in the talks if you have better insights.
no. I think you're doing great. Um, I mean, do you plan on giving an idea about Baron Kuvert's new idea, like new ingredient? That's
The varifold
that
thing,
might be something that people are interested in. Yeah, why? What was Leon Simon missing?
I I don't think he was missing much, but yeah, they have to do some approximation things to make sure it works almost everywhere in the case of varifolds. And again, even I think in Simon's proof, Liao just pops up. If you have like a K multiplicity point, you have a lower bound on the functional, Willmore functional. But I can go through the varifold case if people want.
Yeah, I don't know. I think that it somehow closes. It's just a little thing, but it really does strengthen. I mean, it shows a little bit the strength of what Leon did. Um,
Yeah.
and look, I know it is technical, but if I could make one comment, I would say that this method of proof in this paper, it is so classical and it's so strong. He's really pushing through the very classical difference quotient approximation of derivatives, but in this geometric conformally invariant setting. And it's just showcasing the power of that idea and how it is still applicable even when you're quite far away from, flat PDE on a
Classical
domain in
setting.
Rn.
Yeah, yeah. I'm wondering if I should go through that regularity result for this theorem proof.
I mean, what would be cool would be to say, look, this is the technique, and like it feels very raw, like you're
Yes,
really working
you
with these very basic objects. You're
the
approximating derivatives by difference quotients.
it goes all the way back to like shorter estimates, and the same proof works in this highly technical setting.
Exactly. It's like Schauder estimates, and
Yeah.
I feel like you don't want to go through every term by term by term by term and make people die from like tedium. But on the other hand, you do want to give people some kind of indication, oh, when should I try this technique in my own work? When could this help me get through a tough analytical spot? And that might be to highlight, okay, so this method lets us take this limit, or this method gives us this estimate, which is uniform in this way. I mean, one of the things that Leon's so good at is, like you were saying with the graphical decomposition lemma, he's like, okay, I've got all these constants, but they all depend on things in this exact way. And as long as I've got L1 control of this, L2 control of this, I've got control of the number of these things, I've got control of the number of these things. And
Yeah.
it just makes it's almost like a soft analysis point of view where you've got this kind of loose setup and you're just taking these limits. But then he's also got this tight analytical control. So I
Yeah.
don't know. I don't know how you really package it together. I don't think I've ever seen a good present. I mean, like a intuitive presentation of it. But that's your challenge, Devesh.
Okay. I'll see.
Do we
All
have any
right
real
then.
questions?
Yeah. Right. Well, in the absence of further comments and questions, let's thank Devesh again. All right. Thanks all. We'll be in touch when we decide when the next one will be. It'll be Devesh again, I believe.
Yeah. Maybe 2 weeks from now.
All right. Great. Thanks, everyone. We'll catch you next time.
Thank you.